So the first one, our PhD student Pumika, who did a poster on assessing long-term performance and durability of geopolymer mortar for sewage pipe coating applications. She's actually in Germany right now. So we've got her a certificate here just by proxy. Pumika, just checking if you're online. I did see your name before.
Hello, good afternoon, Polly.
Hey, Pumika. So congratulations to Pumika. I believe it's early in the morning over there at the moment, so definitely thank you to her for dialing in. And congratulations again. So give her a bit of a round of applause. Okay.
Thank you, Polly.
Next up, awards-wise, we've got Molly Hall. So Molly wants to make her way up. Okay. So Molly was in the 1 minute talks as well as having a poster. So she got one of the best poster awards for the centre this year as well. So congratulations to Molly, who's doing the through thickness dielectric sensor work. Okay. Next on the list, we have Janitha, who was doing shape memory polymer smart plaster. And some of you guys may have seen this in the lab as well. So congratulations to Janitha as well for one of the poster awards within the centre. And then lastly, Adrian has gotten the 4th award here, where he had the model aggregate. If you remember, he was in the 1 minute talks as well. So he's gotten the 4th award there for Best Poster Award for 2022. Okay, so congratulations to all our award winners. They do get a monetary prize as well, which I believe has been distributed in advance. So I believe some of the students already had plans for those. Okay, so that was a really nice way to come back from lunch, celebrating some of the work that our students have been doing. I'm going to now hand over to Charlotte Brownlow, who's currently the Acting Dean of the Graduate Research School. So for master's students and for companies wanting to work with research students, this is definitely one to listen to.
Thanks, Polly, and hello everyone. And thank you for letting me come along and just speak really briefly about some of the wonderful HDR stuff that we're doing here at UniSQ. So I am the Acting Dean of the Graduate School. I'm not an engineer, so I won't understand anything about the research that you've been talking about all day. I'm actually a psychologist, so I sit in a very different field. But in terms of research and research students at UniSQ, this is such an exciting time for engineering students. There are so many fabulous initiatives and projects and big research initiations going on at the moment. So it's a really, really good time for you to be doing research. So at UniSQ, we've got 2 primary research degrees. We've got the Masters of Research and we've got the PhD. So similar kinds of degrees in terms of they're both about research and they're both about you following your passions. One slightly bigger with a PhD and the Masters ideally designed for that post-bachelor. I guess the big question is, why would you do it with us at UniSQ? What's so special about UniSQ? Well, we have fabulous people like Polly working at USQ who are doing fabulous work. And I'm sure that you've heard all about the Trailblazer big projects that are really exciting and are really kind of due to kickstart from USQ very, very soon. The other thing that a lot of these big projects are building, which I think is really exciting, is that real link and proper links with industry. So we're seeing a much more focus around internships. So students can get some really good experience working with industry in terms of internships, building up their CV and really showing that kind of practical application. I think the other big thing for students is that with these big projects such as the Trailblazers, there are also lots of scholarship opportunities. So I'm sure Polly's quite happy to share the links to all the scholarship opportunities that are out at the moment. But these are really, really good opportunities for students to really work with industry and collaborate with industry to look at real meaningful research and to actually have their kind of living stipend covered. So I think the scholarships are a really, really exciting opportunity for us. The other thing we're exploring are industry-based scholarships, industry-based PhDs. So industry people out there, please come and talk to us about if you're interested in hosting research and a PhD student that really tackles those core industry problems. So if I share some links with you, Polly, afterwards, you can share them around the various different places. But please do reach out, speak to the academics, speak to the centre directors, come and speak to us in the GRS. We only hide in Q Block just over there. It's a bit drizzly out there at the moment, but do walk over and see us. There's really good opportunities for engineering students and research more broadly at the moment. So any questions, please come and find me. Thank you, Polly.
And just as a quick note, on some of my projects, we have been talking to some of our industry partners, whether they themselves want to do a PhD as well. So for those of you visiting from industry, if that was something you were interested in, we can take a look at that. So that finishes up just the beginning part. I am now going to hand over to Charles, who's visiting from TMR, where he's going to be talking about composites for maritime infrastructure. So we'll just get his talk up. And I'll bring that to you.
That's good. Oh, I'd like to say thanks for USQ, or UniSQ, I should say, for asking me to present today. And thank those in the audience for listening in. As I mentioned, I'm Charles Sorbello. I'm currently the project manager of the Maritime Infrastructure Resilience Project. I'm normally the principal. Whoa, what's going on there? I'm normally the principal engineer coastal at the Department of Transport and Main Roads. The Maritime Safety Queensland branch, who I'll be referring to as MSQ. That's what we generally call ourselves. I used to like the MSQ USQ synergy there, but you guys changed. It's okay. So my background, civil engineering. I completed a bachelor's at UQ in 2010, and then went on to explore structural engineering here in USQ in 2014. Since then, I've been able to put that into practice and developed designs for boat ramps, navigation aids, breakwaters, revetments, and there was a submarine pipeline once. Presentation, if someone could play for me on the department and its features, hopefully good. I haven't seen it yet.
Queensland, home to more than 5 million of you. We're connecting you from A to B by more than 33,000 kilometres of state-controlled road, 6,000 kilometres of rail track, and 130 million public transport trips each year. Our job, no, our passion, is to deliver a network that is accessible to everyone at every age or stage. We're investing more than $5 billion to improve our transport infrastructure, making your roads more flood resilient and bringing new ways to pay, so you can use our network your way. We're making your health and safety our top priority. We're always listening to you, creating more online services than ever, serving customers online over 11 million times each year. We've kept the state moving, transporting more than 1 billion tonnes of freight, adding 27 kilometres of new cycling infrastructure, and building 9 new boat ramps, pontoons and jetties. We're investing more than $1 billion to maintain and improve our network operations. We're recycling over 1 million tyres and using them to build our roads. We're switching more than 35,000 streetlights to smart LED technology. We're creating a transport system that's environmentally friendly and socially sustainable. Investing in skills, creating jobs, and embracing new technology. Queensland, we're here for you, to connect you to family and friends, schools, work and hospitals, to create a single, integrated transport network accessible to everyone.
So maritime safety, I've got a slide here. One of our goals, our main goals, is to reduce the 000, zero accidents, zero casualties, zero ship source pollution incidents. And I think this very much feeds into MSQ's desire for resilient and safe infrastructure. As a bit of a summary of my talk, I should hopefully give everyone a brief overview of some of MSQ's role in maritime infrastructure and the research we're currently undertaking. I would like to briefly introduce the Resilient Maritime Infrastructure Project and also look at some future research opportunities that we see as important in the maritime space, and then provide you a brief update on the national symposium on composite infrastructure that we're hoping to host with USQ at the end of the year. So, as the video showed, TMR is a very diverse organisation. Maritime Safety Queensland is a small component, but in that component, we are a regulatory body and also want to support and grow the boating industry in Queensland. And recreational boating is a big part of that as well. And this is directly and indirectly through supply chains, which support several thousand jobs. The main areas that MSQ deliver infrastructure are the recreational boating infrastructure team, the aids navigation team, and the state boat harbour team. So in rec boating, we deliver and maintain boat ramps, pontoons, floating walkways, jetties, channels, breakwaters, revetments, seawalls, that kind of infrastructure. There are 455 boat ramps across Queensland and several thousand aids navigation. Queensland manages we have 490 wharves and pontoons. And although not directly maintained by the department, we have 18 trading ports and produce 357 million tonnes of trade each year. Part of our network is the state boat harbours, in which TMR and MSQ maintains and owns all the infrastructure there. And it's the boat storage and the facilities in those boat harbours that makes Queensland have a particularly strong boating industry, we believe, in terms of manufacturing boating and the industry itself. Our research projects, as you may have heard, we're very fortunate to be able to host and support Professor Alan Manilow from UniSQ as part of his Advanced Queensland Industry Fellowship for the last 2 years. And we have been able to get GFRP reinforcement into boat ramp planks, which we are now also looking to standardise GFRP reinforced pontoon decks and our floating walkways. One of the projects you can see here down the bottom there is replacing our galvanised steel mesh boat ramp slab with hand-placed GFRP bars, which is a bit contrary to what the normal use would be. However, we're finding there's some advantages just beyond durability with using these bars. We can increase our slab sizes. We can go back to saw cut joints, which are things that we have gone away from over time because of the limitation of steel reinforcement. We've had the opportunity to supervise one of the UniSQ's PhD students. I think Zian is here today, giving us a 1-minute presentation earlier, and we're hoping to continue to expand on that opportunity. We've begun to examine the use of GFRP reinforcement and also composite structural sections to develop more resilient and durable pontoons. These are following the 2022 flooding. And then we're also looking at composite aids navigation. As Alan mentioned earlier in his presentation, TMR is hoping to develop and publish a technical standard on composite reinforcement, MRTS 271. This will be hopefully early next year. So resilient maritime structures. I thought I'd expand on how serious this was for MSQ and the industry, and I guess Queensland as a whole. The early 22 flooding was pretty devastating. We lost tragically 13 lives, and the property damage was thousands of homes impacted, and the calculation at the moment sits at $7.7 billion of infrastructure damaged. 492 million of that was public infrastructure. Not all of this was maritime infrastructure, but there were, hard to quantify, the moment we're sitting at 5.5 or 6,200, depending on who you believe, tons of pontoons alone and polystyrene foam that floated down the river and were found north to Noosa and beyond. So these types of events will likely increase, not only as a result of climate change increasing the severity, but also the density of population. So the Queensland government has produced a 2017 strategy for disaster resilience. And following on from that, immediately after the flooding, a 2021-22 recovery and resilience plan. And this actually requires that we develop new designs and construction standards for pontoons. So I see this as an opportunity to harness the value from a sustainable and effective material such as modern composites to deliver the resilient infrastructure we've promised. So I briefly mentioned the type of structures we build and maintain. However, these are the ones that I think are key. The replacement or encapsulation, I'm not sure if you can see this, but that picture on the left, that's a pontoon hull that's lost its encasement, it's lost all its polystyrene. The rest of that polystyrene is likely on its way to near by now, but no, I'm sure it was picked up. Replacing that with either a composite hull or more resilient wrap material, those are definitely options for future studies. Reinforced concrete piled boat ramps, not something we looked to implement because it wasn't really suitable. But however, it allows you to build boat ramps on beaches. Down the bottom there, it's a little bit of a sketch, but the idea is, can we use GFRP tendons as post-tensioning in marine structures, boat ramp slabs, seawalls, even the pontoons themselves, going away from traditional hinges or joints or rigid links. So I think MSQ is a small part of the department, so we see ourselves as a bit of a link to getting this technology adopted into the wider TMR space where there are bridges and culverts and many, many structures. I mentioned ACES navigation earlier, several thousand. Most of these are steel pile, aluminium top structures. They're high maintenance and they're extremely difficult to inspect. These physically have to be climbed. That one's lost its ladder on the left there. But introducing composites into the piling, building, the aluminium suffers from bird dropping corrosion. It's one of its failure mechanisms. And even small items like you've got the ladders and the lampstands, that one's on a lean there because of literally the corrosion to it. Just reducing the need for costly maintenance and frequent inspections in these really remote locations. Small elements add up to a big difference. So I thought I'd try to take this opportunity representing government organisation to give you an honest perspective from an asset delivery, and I've been in that team, and an asset owner type scenario. One of the things I've noticed is a shift towards people want low maintenance assets. So structures like that steel jetty that's a durable structure if it's painted every 8 to 10 years. So durability doesn't necessarily mean low maintenance, and also the other way around. So the maintenance can be expensive. Painting over water now is something that's hard to do with environmental constraints. You can't be blasting and letting the blast medium and the paint go into the water. But then the next point I've got there was, well, it's difficult to sell an increase in cost over long-term benefits at the moment. So we're in a bit of a situation where it gets done with larger projects, but I think the industry and asset delivery needs to try to work together to change the way smaller projects are evaluated so that the whole of life cost gets incorporated, not just the straight up construction costs, which is what is currently focused on. My next point is something I think UniSQ do really well by having us here right now is collaborating with the industry and the fabricators and the customers, because I think it's not just about getting the numbers and strength of material. Yes, that's important, but I think it's all about confidence. If industry is confident to invest in, to use products, that's very important. There is substituting something I've found is a bit harder than using something in a new way. So the example below there is a barge boat ramp combo, and that was really made possible in that configuration because we used stronger GFRP reinforced piles. We've also built glass fibre reinforced pull-truded section fixed walkways on boat ramps now. It's like a hybrid between a jetty where the landings go into the water. These sorts of things wouldn't traditionally be thought of with standard materials. So using new materials and new ways, I find, is easy to sell than saying I'm just replacing something with something slightly more expensive. I just thought I'd throw this one in here as a bit of an extreme case, what we do. However, this shows that we're really building these structures in remote locations and they're very environmentally sensitive. And this one here is reinforced with GFRP bars. And we're expecting this to be low maintenance and have a long service life. So finally, just putting in a plug for the National Symposium on GFRP bars. It's a joint collaboration with UniSQ. And I think it's an opportunity for the industry and the experts to get together, try to help align what the priorities are, what's currently possible in the industry in terms of manufacturing or supply chains, and then what can be locally manufactured, and then try to build that industry confidence to get products locally manufactured, because that's often the first question I'm asked when I introduce a new material in the design is where's it made? Can it be made here? So getting this industry together at this event. This is on the, sorry, it's a bit hard to read, the 30th of November. And it's being held in Brisbane in the Maritime Safety Queensland headquarters. And ultimately, it'll act as a way for us to narrow down what research is required. And that's it. And thanks, everyone. And please feel free to stay connected with the department other than registration renewals. Yeah.
Thanks, Charles. Just checking if we've got time for one or two questions for Charles. I know we're running a bit behind, but anyone has a burning question? Yeah. I just had one burning question. So you talked about maintenance of assets if they were steel and so on. Has the maintenance of, and Alan may have touched on this earlier in the day, has the maintenance of GFRP assets been determined yet? As in, how often would you need to be monitoring, maintaining, etc., or is that something for the research into the future?
The idea is that we are trying to make them maintenance free for the design life. The design life of maritime structures isn't as long as people may think. 25 years for floating infrastructure, like traditional recreational floating infrastructure, and then 50 years for things like a boat ramp. So a lot of the failure happens around the structure's interaction with the environment physically more so than deterioration sometimes. Yeah.
Okay, no, just a thought. Okay, so next up we have Geoff, who I believe is online. Geoff, just checking that you're there at the moment.
Yes, Polly, I'm here.
Excellent. If you want to share your screen, and you should be able to drive from your end.
Let me just
wait to see it. Okay, we can see you.
Okay, if you can see, let me bring up
your slides up, and away we go.
This is the first time I've done this. You'll have to excuse me if I mess this about a bit.
And just as a note, some of you may have seen this on the program, but Geoff is going to be talking about a better plastic waste solution. So just as a note, Geoff is one of my collaborators, but he has a background in fibre composites and various other things as well. And in this instance, he's focusing on mixed plastic systems.
So Polly, is that slide up now?
No, sorry, we can't see it from this end.
What have you got? What are you seeing at the moment?
We're seeing you. Just a second.
That's lovely. Okay, let me go share screen. Okay, you've got a slide now.
And just into screen show mode.
Yeah, I'm just going to go to slideshow. How's that?
Wonderful. Away you go, Geoff.
Thank you. Okay. So thank you, people, for entertaining me this afternoon. I thought I'd start by sort of saying, look, the title is You Can Make Other Things Other Than Plastic Products from Plastic Waste. And we've collected plastic waste for a very long time now with remarkably little success. And let me just bring up the sad reality. Currently, 92% of all our plastic waste collected goes to landfill. So all of you people who are washing out your yogurt containers and putting them in the recycling, about 92% of that is going into landfill. And so what is being collected is normally clean drink bottles, PET bottles. 92% is about the world average. Europe does a little bit better. America does about exactly the same. America was doing much better when they were sending a lot of stuff to China, but when that got canned, they fell back to about the same as us, about 92 to 93%. Companies that make things from plastic genuinely don't want recycled material, even if it's free. There is a big problem with making, well, let me rephrase it. I'll expand on this, but take that as a given for the moment. There's government legislation and all sorts of packaging requirements that make it extremely difficult to use recycled plastic in food packaging. The quality standards or the cleanliness standards you need for plastic to be used as food packaging generally prohibits any sort of recycled material. And it sort of doesn't matter how you sort the waste, because it's never going to be good enough. Now, I'm sure there are people in the room who are looking at those statements and going, you know, how can I make such bold statements? But let me start by having a little primer here. Let's look at 2 reasons why we don't use plastic waste. And that's number 1. That is a pretty standard injection molder. It's a very expensive piece of kit. It's a very touchy piece of kit. It does not like contaminated materials. If you mix your plastic, so you could have 1.5 tons of polyethylene, you need about a cupful of nylon and it will stop this machine. And that's now a couple of hours of pull down, if it doesn't damage the machine entirely. But assuming that it doesn't, then it's half an hour, a couple of hours of taking it to bits. If you have any metal or sand or bits of shell or grit or anything else, you could really seriously damage this machine. So the question is, when you're offering recycled plastic to an injection molder company, how cheap does it have to be for them to risk damaging this machine? And currently raw virgin polyethylene is about $3.80 a kilo. So if you're thinking you're going to have to get under that, you're going to be, what, $2 a kilo, $1 a kilo? And even then, they're probably not going to risk their machines. The second problem always surprises me, reason number 2. I really struggle with recycling plastic that is colored. Almost all plastic has a color. Milk bottles are probably the only thing that don't have a color. And the brands are really, really fussy about their colors. This is Coke Red. It's a Pantone 484 color. Pantone is an international system for color in manufacturing. They don't accept 486 and they don't accept 470. This is 484 and they mean it. If you deliver a million of these bottle caps and they're the wrong color, they will reject them. And that's pretty much true for all the major parts. All the plastic parts you see, just walk around and, you know, the top of your washing machine, the plastic cover on your space heater, all of these are carefully designed colors. And they're not prepared to go random. They're not prepared to go, okay, well, if you just happen to have a whole lot of plastic waste that is lime green, that's fine, just send us that. So you can't uncolor plastic. Once it's a color, it stays a color. So unless you want to recycle everything down to a sort of muddy brown, sometimes black color, pretty much you can't select your colors. I'll just run this little video for you because it's kind of, if it runs, it's kind of instructive. This is a sorting line at a recycler. The important thing there is all of that plastic waste on that conveyor is going to landfill, except the stuff they take out. And you may have noticed in this very short video, they didn't take a lot out. Again, they're looking for clean PET only for this recycling. Sorting. So there you can sort of see the problem. How can we sort plastic waste into type, of which there's a dozen different types? Quality, in other words, is it too contaminated to use to have oils or sand or grit in it? And color, and get anything like a commercial quantity. So here's your next problem. If you're supplying to a company that's going to make a part for you out of plastic waste, they want a reliable supply of Pantone 484. Well, you can't guarantee a reliable supply of Pantone 484. This month, it could be something. Next month, it could be something different. Essentially, that's what the no waste program with USQ is about. We have to change the thinking that plastic waste is still plastic. It sounds kind of crazy, but the fact is that plastic waste is a cheap, readily available raw material that can make all sorts of things that you would never think of making in virgin plastic. But to do that, you have to change, basically forget everything you know about making parts from plastic. You can't use injection molders. You need to use the plastic in large quantities. You need to use thick walls. There's all sorts of design restraints, and I'll show you some examples of this shortly. There's also, we need a process. Because we can't use injection molding, and injection molding is like the go-to for plastic molding, then we're going right back now to a process that was used before injection molders. So this is like what they call transfer molding, but this is a process that goes back to the 1920s when they were using Bakelite. It's a good process. It's just not as efficient as injection molding, but it allows you, the critical thing is that it can be highly contaminated. It's not a twitchy multi-million-dollar machine. This is a little bag of what we call post-consumer plastic waste. And there's everything you can imagine in here. Bulk of it, probably about half, is some sort of polyethylene or polyolefin. They're a low melt plastic that can be used to consolidate the rest. The problem is there are different melt temperatures. So by the time you're melting nylon, you're burning polyethylene. So there's no one temperature which will give you a really good melt on all the plastic in that bag. This is a part that we made, which is a consolidation. So this is a mix of post-consumer plastic, the stuff you saw in the bag, shredded down and pressure molded into this is a tray. And you can see the sort of mix of colors. And if you look at it closely, you'd see a mix of plastics in there as well. So there's all sorts of, there's ABS, there's polyethylenes, there's PET. And this is an interesting part, but it's unreliable. And it's unreliable physically and in terms of color. So even if you think that's the prettiest thing you've ever seen, the next one is going to be completely different. And so as an art piece, kind of nice. As a commercial prospect, not so good. The other problem is that we have plastics that don't melt at all. And those are the sort of vacuum metallized polyesters, so, chip packets. And if you get a couple of those lining up on this part, the corner will just snap off in your fingers. So that you can't rely on it in terms of structure. So we were looking for a solution to this, and we have a background in fiber composite. So what we did, we said, okay, well, let's just use this melange of multicolored plastic as a core material and wrap around it some structural elements. So here you can see a rod that we make. This is a 60mm rod, and it consists of the core, which is that multicolored stuff, stuff in the middle, surrounded by a flax, a 200 GSM flax material. And that flax material has been impregnated with recycled plastic bags. So the whole thing, all the plastic in this part is post-consumer waste. But this is a highly structural part now. This is a part that we can rely on, both in terms of its look, it will always look that way, and in terms of its structure. You can actually make structural parts from this. This is the same panel you see, which has been wrapped in, this is a woven linen. You know that it's been using post-consumer bags because it's covered in the warning labels. You know, please don't give this bag to a small child. The warning labels are actually a problem. The type of dyes that they use on those printing those labels doesn't interact well with the plastic. But that's a very effective use of the material. Here are a couple of other parts that we're running. We have a raft of new parts, but unfortunately they're not quite ready to show anybody yet. Probably the one on the left, that green tray you see, is just hot folded. So that's impregnated flax, which has been heated and folded to create a tray. That again is just using recycled plastic bags. The one on the right is kind of more interesting. That's a part that we're doing for Country Road, and that is a tray. It weighs about 1 kilo. It uses a lot of plastic waste. It's not that big. It's about 200 millimeters by 110 millimeters or something. And again, this is using rejected fabrics from Country Road as well. This is the first test part. We've since moved on to much more complex parts and much bigger parts. The current one we're making weighs over 1.5 kilos. And you need to, this is what I mean about you've got to change your thinking about using plastic, because not many plastic parts ever weigh that much. The whole idea is to minimize the amount of plastic, to reduce the amount of plastic. In our business, because we get paid to take the waste, we want to use as much plastic as we can. This is our project number 1. This is a street pole. It's a 60 millimeter pole. There are 4.4 million poles like this in Sydney. Currently, they're all galvanized steel, which the picture on the left, I mean, you might find that entertaining, but that we put that pole in the ground. It was there for less than maybe 5 minutes before that dog came along. This is a great use for using up large quantities of waste. This pole is corrosion resistant, it's tough, it's durable. We can do it in all sorts of aesthetic colors and blends. And once you're sick of this pole, we would shred the thing down completely and it becomes the core of the next pole. So it's 100% recyclable. The economics of this, it's a tricky one. The reality is that how good is a business where your raw materials are free? And how much better would it be if they pay you to take it? Diversion to landfill actually attracts government subsidies. The problem is you've got to think of something to use it for in volume. You know, there's plastic waste is measured in tons. And so as a business, it's actually quite viable. But unfortunately, there is if you like, a technology gap. There's no one who has these processes yet who can make parts this way. I'm going to just, how are we going for time? Okay. Part of the program that we're running with USQ is to ultimately move this technology to a village level. That is, currently we're picking up plastic and trucking it all over the countryside. We take it to these central repositories with the idea of reprocessing. And the problem with that is that it becomes an exercise in logistics. So what we're looking at is, can we reprocess plastic into a viable product used at a local level, and then make the machinery simple enough and cheap enough to basically every small community can reprocess their own plastic waste. Essentially, that's the collaboration that we're doing with USQ on the No Waste project, trying to bring this technology into a finished article that is useful to a small community, with the aim of empowering them to reprocess their own plastic waste. As of last week, we're now in discussions with both Fiji, the Philippines, about setting up a local LPM project. So we have visions of this far beyond just what we're doing in Australia. So I'll now throw you open. I'm sure that's opened up some thoughts. I'll throw it open to some questions if you have any.
We have time for one or two questions if anyone has any for Geoff. We've got one from the front, Geoff, and I know this guy's in aerospace, so this should be interesting.
Not really, it's only just. The outer structure that you've got for the poles, does that take care of I assume that the polyethylene and all those sort of things by themselves would have a fair bit of bend over that length, that outer structure. Does that give it the resilience it needs to be able to hold together as a pole?
Yeah, we were genuinely surprised because we've done our 3-point bend tests and we expected the thing to fail in that sort of progressive plastic, creep mode failure. But the fiber orientation, it was surprisingly stiff, and its failure mode was catastrophic failure, like you would see almost like you'd see in a carbon fiber part. So it's not a floppy plastic pole by any means. And the choice of matrix, I mean, we're using a polyethylene matrix, which is probably the most flexible of anything you could choose. You could do it with recycled PET at a much higher temperature, and that would give you something, approaching an aerospace part. But no, it's surprisingly stiff.
Yeah, because I asked the same question earlier this year. Okay. All right. We are actually back on time. So I'm going to throw over, Danuki's going to put up a video from our next speaker. So our next speaker is also one of another project focusing on clean energy. So we've got Trevor Powell presenting this video, who's the CEO of Impacts Renewable. So Danuki, I think you can hit play and we should be good.
Good afternoon, and thank you for joining us. My name is Trevor Powell. I'm the Chief Executive of Impacts Renewable Energy, and as the name implies, we're a renewable energy specialist. And I'm here this afternoon to talk about clean energy and our relationship with the University of Southern Queensland. But before I do that, I'd like to welcome you all to country and acknowledge all those that have gone before. And what I'm going to do is read a brief excerpt from the Statement of the Heart. We're all children of this land and we must respect it. And what the statement says is that we are all tied together, an ancestral tie between the land or Mother Nature and the Aboriginal and Torres Strait Islander peoples who are born therefrom, remain attached thereto and must one day return thither to be united with our ancestors. Spirituality is a deep-seated notion of the heart, and our place in the world and our use of energy impacts that spiritual relationship with the land that we live in. This was the system that was used by our great-grandmothers, combined heat and power. And I can still remember growing up in Australia in the 1960s and 1970s, collecting firewood from out of the bush so that my mum could go and boil the copper so she could do the washing and hang it out on the clothesline out the back. Times really have changed since then, haven't they? Our societies are dependent on energy. We harvest and consume energy in almost every human activity, and we're energy junkies. Our world cannot survive without a constant supply of energy, and that energy source today is slowly killing us. And I want to talk about 7 key points in our discussion this afternoon. The majority of global energy production is derived from fossil fuels, and in fact a full 80% is based on fossil fuel production. Half of that is produced by China, the United States and the Arab states of the Persian Gulf. And the Gulf states and Russia export most of their production, largely to the European Union and China. Now, not enough energy is produced to satisfy demand. Energy production increases by around 2% per annum, except for solar and wind energy, which grow by between 12 and 30% per annum. As I mentioned, not enough energy is produced to meet demand, and also Note that Russia is a big exporter. We'll come back to these points shortly. This is the world as it is today. Conflict is not going away, and we're likely to see more authoritarian regimes and dictatorships. Think of Belarus, Cuba, China, Egypt, Iran, Myanmar, North Korea, Russia, Saudi Arabia, Vietnam. There's about 50 countries, depending on how you count them, and some others are going down the path. In our own backyard, for example, the Solomon Islands, when you consider the outside use of force to quell discontent, the restriction on local press and media and banning of outside critics, and other countries like Sri Lanka are on the verge of collapse. Most conflict is either ideologically driven or a battle for resources. Ukraine is a battle over resources, with one country, or rather their dictator, trying to claim more. I asked you earlier to note that Russia was a big net energy exporter and has been accused of weaponizing energy. And now that the horse has bolted, you can expect to see energy used against anyone that doesn't agree with Putin. And all the flow-on effects to the global community and other suppliers with monopolies, and will start to impact all of us. There's a sort of religion about clean energy. However, when you break it down, we could set a criterion so that we're talking about the same thing. So to compare disparate technologies, energy yield, cost to energy yield ratio, direct usability as heat or electricity, manufacturing inputs, life of technology, end of life recycling, in-service liabilities, cost of operations and maintenance. The length of supply chain has become a quite significant issue thanks to the pandemic. What we can say is that solar heat for industrial processes doesn't suffer from losses due to conversion to another form. In other words, PV, where you convert light to electricity to heat, is essentially a very inefficient process, whereas heat can be collected from the environment. And like as the man from Mitsubishi says, please consider the true cost, not just the dollar value on the bill.
Time is against us. I only have time to discuss one later. Let's talk pitfalls.
Let's now take a moment to have a look at electric vehicle and electric batteries. You see the photographs on the right are a series of battery fires. The first one is in Victoria. It's a battery factory. The middle one is a Tesla Model S on fire. That's an expensive experience for the owner. And the bottom is a bus fleet. Now, these batteries combust spontaneously with no warning. And insurance companies are creating policy exclusions around battery use. Now, lithium batteries are a step, but they're only a step. They're not a viable long-term solution. And I note that UniSQ has a summer school battery research project to try to find a better way of doing this. And it's worth noting as well that there are multiple different battery chemistries and technologies. Nickel iron is a particularly promising prospect that was developed over 100 years ago. Flow batteries are again a different type of battery technology. So whilst the world is at present looking at lithium as the solution, it's just one of a number of steps. California is building the largest battery in the world near San Francisco, and they intend to power it from solar panels and windmills. The claim there, of course, is this is the ultimate in being green, but it isn't. The construction project is creating an environmental disaster, and I'd like to tell you why that is. The main problem with solar arrays, solar panel arrays, is the chemicals needed to process silicate into silicon used in the panels. To make pure enough silicon, it requires it to be processed with hydrochloric acid, sulfuric acid, nitric acid, hydrogen fluoride, trichloroethane, and acetone. And in addition, the solar panels need gallium, arsenide, copper, indium, gallium diselenide, and cadmium telluride, which are all highly toxic. Silicon dust is a hazard to the workers, and as we said previously, the panels can't be recycled, and they're making their way into landfill. That is a major, major environmental problem in the making. There's a lot of misconceptions about the various renewable energy sources, and there's an underbelly, a dark side, if you wish, about the environmental impact of technologies that typically we understand to be green. The photograph on the left is the final resting place of a field of wind turbines that are going into landfill. Now, windmills are the ultimate in embedded costs and environmental destruction. And there's a value system that needs to be understood. Each windmill, a large-scale windmill, weighs almost 1,700 tonnes. That's the equivalent of 23 houses. It contains about 1,300 tonnes of concrete, almost 300 tonnes of steel, 48 tonnes, 50 tonnes of iron, 24, 25 tonnes of fiberglass, and there's numerous rare earths that can't be extracted. I can't even pronounce the word, so I'm not even going to try. The blade of each windmill weighs 81,000 pounds. That's nearly 40 tonnes. It will last 15 to 20 years, at which time it must be replaced. We can't recycle used blades, and we can't recycle the fiberglass that's used in their manufacture. The photograph on the right is a wind turbine on fire, the engine housing. And the firemen simply couldn't put it out. They couldn't reach the 100 metres up in the sky. So there's numerous problems that still need to be resolved. Impacts is currently working with UniSQ to develop and commercialise what we call a SEWA technology, solar enhanced waste energy recovery. What happens here is that the high temperatures that are reached by our concentrated solar thermal collectors enable the SEWA technology, and that will allow us to supply a high value, benign, transportable solid or liquid fuel from organic and municipal waste, from waste effluent, capturing carbon, also at the same time destroying pathogens that are normally allowed to bioaccumulate in the environment. SEWA is a waste to energy solution which will help clean up the environment of human activity and waste, and it's a good but, it will be containerized and therefore could be distributed to those emerging economies where waste currently flows down to the sea. And therefore that reduces the growth of the Pacific waste island and provides opportunities for creating income for communities and reducing their dependence on cheap fossil fuels. In developing the SEWA technology, the role of the university is to prove the model, to identify the best types of waste organic materials that are both agricultural and municipal for conversion, identify the most suitable method for converting them into a solid or a liquid fuel, identify the quantum of energy required to convert and the yields of the end product from that source material, and the methods of moving from a batch to a continuous process. From that early analysis, from there we'll build a batch processing version for field trials with our council partners. We've partnered with a number of councils around the southeast Queensland, and after that we'll build continuous processing versions for large-scale operations which will be containerised. Once we've done that, the result is we'll be able to clean up waste worldwide and reduce dependency on fossil fuels. CSIRO Chief Executive Larry Marshall says 40% of the technologies needed to get to net zero are yet to be invented. And he labels the transition to a carbon neutral future as bigger than anything we've seen in our lifetimes. I'd argue it's bigger than anything we've ever seen in human history. Dr. Marshall said the monumental task had to be achieved really fast and would require a new level of innovation by business. He referenced a 2019 paper published by CSIRO that mapped the pathway to net zero emissions with 40% emissions reduction by 2030, similar to the targets proposed by the Albanese government. It's largely the plan that the government has adopted moving forward, which is great because it's based in science, but it requires us to invent some things to get there, he said. About 40% of the things we need to get to net zero have to be invented. This country has the power to invent those things. If you think it's hard, you're right. Dr. Marshall said a problem was Australia was scared to let go of the traditional strengths in the resources sector, which has propelled economic growth. We have an amazing economy, 30 years of economic growth goals by resources, and we're afraid to let that go, he said. And most companies are stuck in the same boat. But we can actually use science and technology to invent and innovate a much stronger economy, a much better future, but we have to overcome the fear to let go of what we've already got and invest in something a little bit more risky. And personally, I don't mind that at all. We've almost finished, but before I go, I'd like to put a question to you. And that is, what will it take to make clean energy a reality? For chief executives and GMs, it means you need to know more than just the gross number for your energy costs. It means you need to know what form your energy is bought in. Does it come in the form of coal, LPG, natural gas, diesel or crude oil? And you also need to know how you use your thermal energy. Do you use it for heating, cooling, freezing, air conditioning, hot water or steam? Then you need to be able to consider what clean energy alternatives exist and what's available to you for your existing business infrastructure. What can you do in the future with your strategic planning? If your business is expanding, what opportunities could a new site provide? Clean energy is more than a financial gain, it's a marketing coup. Improved environmental credentials is more than just an increase to the bottom line. It can be an edge over competitors. Your shareholders, your customers, your business partners, and our government is demanding and supporting renewable energy transition. So the question is, are you going to be ahead of the curve or behind it? Concentrated solar thermal energy is not PV. We can't meet industry's needs for heat by simply bolting on more PV panels. Impacts is a concentrated solar thermal specialist, and CST is simply more effective, more efficient and cheaper at producing process heat and steam for business, whether that's for cooking or cleaning or whatever the end use, directly from the heat of the sun. No PV required. I'm not here to pitch our product, but I want you to think seriously about clean energy and about making a difference. Neville's the bloke up the back in the red shirt, and he will talk to you for as long as you like about concentrated solar thermal energy. I'd like you to think about meeting international targets as a country, about our national goals, your commercial goals, putting forward real green credentials and getting your story out there. The government will even provide funding for those that are first in class, for research, for early commercialisation and for best practice. The challenge for political leaders is to be brave enough to take chances by providing support and funding on long shots, not just on the safe bets. Not just the large corporations that can provide dollar for dollar funding and have large teams of writers to complete the R&D bid, the support of lobbyists and simply having the resources available to make things happen. But it's actually to provide support to the small entrepreneurial companies with the capacity to make dramatic changes to the world around us. Impact's team is distributed across Australia and Neville Fox is here to take questions. Business cards and brochures are available, and please feel free to visit our website or contact us at any time. Thank you for listening.
Okay, so we had Trevor do the video because he's actually New South Wales based as well, like Geoff. Just checking if anyone has any questions. I always say my speakers are sometimes the most controversial, and there was a fair bit to think about. Just checking if anyone has any questions relating to energy. One thing I will mention is we are focusing on the solar thermal energy, which in amongst the mix is probably still in its infancy and uptake. And so exploring that area in particular within a suite of projects as well. So in the interests of time, I think we'll leave it there if anyone doesn't have any questions. Otherwise, you can approach Neville and ask him all sorts of interesting questions about impacts. Okay. All right, Danuki, I think next up is me. Okay, so, all right. And we'll just go to full screen in a second. Okay, so I'm Polly Burey. I introduced myself earlier in the day during the 1 minute talks. So this area of the centre is probably the newest area. We only just got going at the beginning of the year when we had two major programs get up in terms of funding. So I've got one program, which is the No Waste program, and that's a multi-million-dollar project. And the Simple program is about to get going as well, also similar in size. And because of these two major programs converging, we established an area within the centre which is focused on sustainable industry design. And I was quite happy, Joyce, I think had an underpinning theme today, focusing on sustainability. So we've seen that in aerospace, we've seen it in civil infrastructure, we've seen it in various other capacities today. So this talk is probably a bit more of a broad view of what we're doing within these two programs and just getting underway as well. So hopefully you've enjoyed all the talks, but I did want to point to some of them that do relate to this area of the centre as well. And you've just had Geoff and Trevor have their talks too, as a couple of our partners, and we do have a few across our programs as well. And so there is a focus not only on cleaning up material and processes that are currently causing environmental problems, but also creating materials that can be sustainably derived and constructed for a few different applications as well, some of which are listed there. So I'm going to probably brush over this real quick because a few people have thrown up statistics today, but this is partly what drives what we're doing. So Geoff put up the post-consumer waste, and that is one area that we are focusing on. But second stage, which I'll talk about for one of our projects, will actually involve in getting into the technical design of particular products to be not only mechanically and thermally recycled, but also looking into the future for chemical recycling in a few different novel ways as well. So these are some of the stats. We still generate a heap of millions of tonnes in Australia every year. These are just Australian statistics. For a country with less population than the UK, we generate more than 1 billion coffee cups. So some of you may have went down to the lab or noticed the particular cups we were using today, which is actually used in one of our sub-projects within our programs as well. Geoff touched on the plastics, the mixed plastics. One other area is e-waste and all the problems that are associated with that. And the space is changing. And then lastly, food waste. So that's probably more my area. And still, we have 1/3 to 2/3 of food that is produced, wasted every year, and that has not changed for quite some time. So it's still a major issue. And as part of the Oceania and US stats, we are probably one of the worst in terms of wasting material. So there is a lot of room for improvement. One of the things lately that is causing a little bit of angst for people, because there's now a lot of rapid policy change statewide and federally as well. And so this can be a little bit confusing. So I had one of my external partners who we're bringing on to one of the programs look at the New South Wales EPA and say, you can no longer send compostable coffee cups to the FOGO stream, which was the intention for them originally. So where do they go now? Do we no longer use what is called compostable cups? So this is creating a little bit of, we're not quite sure what's going on, but hey, we've got to figure these things out. Okay, so I mentioned this area, theme area within the centre. So I will point out up the back, we do have the brochures for the centre in the form that it is right now, and this is the theme area here. So this is sustainable industry design. It's touching on all of the things that some of the speakers that have been covering today. So number one, we are looking at future supply systems for a range of products. The other thing that we are focusing on is the circular material, product and process design. So Jessica's work, where she did the 1-minute talk, is really looking at modelling what these sorts of pathways are, what's the energy usage, what's the social impact, etc. So on, before we jump into something where we suddenly can no longer use a product because of turnaround in policy, we need to look out for these things. Thing is, along with all this research and all these technical developments and so on, we need to make sure that future workforces who work in these spaces know what the challenges are that they're going to face and the kinds of skills that they need. So I'm aiming this a little bit at the Masters of Engineering Science students who will be future workforces in different capacities, depending on the disciplines and that you are currently studying and the interests that you have in future. And then we've got the bits down the bottom, co-design and systemic change. So I think historically there's always been a lot of good research that goes on, but the way that really causes it to be put into practice is actually working together. So we have a long history within the centre working with industries. We've got some of you represented here today. And within our team, we definitely work side by side. So I had one comment earlier in the year, they said, oh, normally we We give our stuff to a university, they do whatever they do and they pop the result out. And they said they'd never quite had an experience before where everything was shared as it was developed as well, and having a bit of ownership into that too. So that's one thing there. In terms of programs that sit under here, so some of the work that was mentioned earlier today, let's see if I can see Tom, but we've had the Railway Sleepers project come in under here a little bit along with Civil Composites. We have the two big programs, the No Waste project and the Simple Hub, which is getting underway, and green geopolymer work has come under our area as well. And to be able to solve a problem that's like this, or some of the pictures that we've seen today from other industries, requires quite a lot of disciplines, experiences, and skills. So I'm going to delve mostly into the No Waste project. So this was our last project, which got funded end of last year. I think we've got some of the partners in the room. I'm staring at one of them right now. And probably a key aspect of what it is that we're trying to do, we're trying to move towards a future across many supply systems, not just one, towards no waste or material that has no purpose or no pathway. So we want to move away from that. There are 5 main streams within the No Waste Pilot Precinct, but it is a bit of a playground. So if you're not quite sure what can be done with your current waste material, there is a little bit of a chance to pilot things, have proof of concept work done by some of our summer and research scholars, which I'll talk about when I get to the education suite. I've already mentioned the circular economy model, which Jessica did her 1-minute talk about. So I'm going to skip over that because I've got another slide. And then the 2 bits down the bottom are all about putting in place pre-processing infrastructure, microprocessing infrastructure where it's needed. So a big focus of this project is setting up local circular economies, because sometimes it doesn't make sense to send a small amount of material way across the other side of the country to be dealt with. It often makes more sense to have it locally dealt with and have a pathway where it is still of use and won't go into landfill. Okay, and then probably the other thing is thinking about different ways of doing business. So how do we collaborate to train, to set up a process, to set up a new industry, and what are the business models that we might need for things to smaller to large scale as well? So pretty broad program, and there's a fair bit of stuff going on under it. So the pilot precinct is broken up into 2 tranches. So we're currently in tranche 1, funded by the Department of what is now called Education. And that set us up for the first 2 years, spend a heap of money, do a bunch of research. If you're doing well, we're going to give you even more. So there will be a tranche 2 if people are interested in inquiring how they might become part of that if they've got something that needs to be dealt with to prevent waste. Okay, so this is just a little bit of a mix of different aspects, and we've got one of Geoff's pictures up there. So he published within the Society of Plastic Engineers, Australia, New Zealand publication early this year about some of the preliminary work that he's been doing under the banner of No Waste and under the banner of some client projects as well. So this is already going to prototyping and potentially commercialization very soon. So one of the challenges we have, which Geoff brought up, is that in some of our material recovery systems, we have mixed materials. And it takes a lot of effort to then separate them out, get nice pure streams, and then put them all back together in all sorts of different ways that we want. So sometimes it makes sense just to use the form of the material as it might be, maybe not expend as much effort and still create a good product. So who, and the coffee cup thing is just a really basic example. Who went and saw the coffee cups being pressed in the lab? Did anyone go check it out? Okay, so in that instance, the usual inclination is to break it all down, mush it all together and stick it back together in different ways. In this instance though, we set Matt a bit of a challenge where he used the structure of the cup, put it together without too much being added, and created a product that could potentially be viable and has structural performance characteristics, which is quite promising. So that's one aspect of it, mixed systems. We can go the old route of separating everything, but there's a lot of work being done in that space anyway. We are focusing on particular pathways in circular economy, so the reuse, remanufacture, etc. So the pathways that have the least impact, we hope. I mentioned collaboration is a really big part of what we do, and that is a small version of a diagram I'm going to show in a minute, so I won't do that. And product design plays a massive part in what we do, because in some instances we're creating things that people haven't really created before. And so this is, in the two programs, probably more of our creative project, where we design brand new things, which people are not doing currently. Geoff already did his talk, so I'm not going to do that. I'm going to touch on the last one, which a lot of speakers today actually talked about. And one of my team members joked a while ago that standards are the bane of innovation. And that's because sometimes it is limiting what you are able to do because you're tied to specific standards. So one that Geoff likes to talk about is street poles. And he says part of the standard says they have to be galvanized, which means straight up you're limiting what your material of use is, which is why he's having all sorts of interesting adventures trying to get through his more mixed plastic fibre composite, which still performs the job, but doesn't fit the existing standard. So there's quite a bit of work there in developing what those might be. And I know Alan's had quite a bit of experience himself with the railway sleepers and various other projects. So that's probably one of the main things that we need to focus on, prove that it works and get it into practice. Okay, so this is the collaboration. So normally you have an industry university collaboration. You may have other partners. We have university, industry, local government, schooling, vocational ed. I've got Roger sitting in the second row. And we have two different operating environments. Now, Toowoomba is probably our main test environment. And I've been told by a lot of industry collaborators, they love testing things in Toowoomba. And I wasn't quite sure why. And they said, oh, it's a really good testing ground. You've got a nice population mix. You've got a few different community aspects that are really helpful. They test ideas here and then they scale them up elsewhere. So that's one advantage we have here. The other partner that we have from a local government perspective as well is Ipswich City Council. And not everyone may know that Ipswich City Council handles almost half of the waste material generated in southeast Queensland. So we're touching on the sort of small pilot scale and then massive scale as well with our modelling work. So in tranche 2, we'll be making the Ipswich component a bit more of a focus as we stand out as well. So that's who our partners are. I've got some little clouds there as well. So we do have CSIRO on our advisory committee, various other well-known organisations in the waste space as well, to let us know, are we doing things that are of any use, and whether there are other people that we should be talking to and partnering up as well. And we do have one advisory committee member whose main focus is on the commercialisation aspect and evaluating what we can take forward. Okay. And the reason why we do all this, and I always get sort of teased about my cast of thousands, is that without considering the viewpoints and the challenges of these different parts of the ecosystem, we will not have any change, okay? We won't have any significant change. We'll have little baby steps, but we won't actually make massive change without making sure the right parties are involved. Okay, so Jessica's poster had this diagram on it. So this is the framework for our circular economy model. We are setting it up, or Jess is setting it up, that she can run any kind of resource or product through it. There are just certain characteristics we need to know. And the point of this actually is having it apply to different operating environments. So we're quite happy to test things through the framework if anyone has ideas. We will be making it adaptive. So if there are any system changes, so the way that we collect material, the way that we process, a new factory gets set up and that changes everything, it is set up that those modules can be put into the model component, which is in the middle. And the point of this is hoping that it will properly inform any decisions made and any further strategies as well. So probably one of the real major challenges of setting this framework up is how do we tie, and apologies for anyone who's colorblind, but how do we tie those red, green and blue parts together, which are the social aspects, the environmental aspects and the economic aspects as well in a model. So normally some of these things are qualitative, some of them are quantitative, what do we do? So this is probably one of the core parts of our project. Jess has been focusing, first of all, on one of the streams, or two of the streams actually, that are really problematic nationally, which are plastic and glass. So one of the things that always befuddles me, did anyone grow up when milk bottles used to be collected back when they were glass? So they weren't sent off and broken down and melted down. We spend all this energy and then we make another bottle again, okay? What we used to do is clean, sterilize, and reuse. And there are countries that are doing this. So Germany is well known for having a reuse system set up. Here we have everything goes in a big mixture, then we're going to take it all apart, and then we're going to reconstruct what it is that we want to make. And as you can imagine, this is effort intensive, it is energy intensive, and there are various other things. But it is currently kind of working because there's been investment made in this space. But that still leaves a bunch of material which cannot go back to these bottles. So what are we going to do? Several thousand tons, maybe more. What do we do with those? So that's one of our first test cases. And there are some interesting things that we're taking a look at in terms of pathways for these, and how the colour actually influences what performance pathway, because that does have an influence chemistry-wise on how it holds up in different environments. So I mentioned that whole societal, environmental, economic, and resource value. And Tom's talk really resonated with me this morning because he says, often it's always been the economics, but nowadays there are other aspects that people are really paying attention to, even though it may cause a bit of extra investment. And where this is coming in, obviously in the environmental and social impact as well. So what actually is value? Okay, to make it viable, it does need to have an economic feasibility to what you're doing, because otherwise you're going to be lost. You won't even be able to do it. But some of the things that can support this, what are your actual environmental impact measures? How do they fit within current legislative frameworks? And how does that support what you're going to do as well? So value may not just be dollar value, it might be resource value, the value of doing the right thing, various other things. But how do we measure those? That's some of the challenges. So I'm going to quickly move to this bit here, which is the education program. So this is a real key piece. So one thing I will mention, we are going, and it's not just year 4, I taught year 5s about fiberglass a few weeks ago, and then being able to determine whether something was made of fiberglass or not. So 5-year-olds are pretty switched on, actually. So what we do, we have a primary secondary program where we actually support students through their science fair or STEM fair projects for the year. So we have one activity, they come on campus, they learn a whole bunch of stuff. We go and actually see how they put that into practice within their STEM fair projects. Last year we had, and I keep mentioning the younger ages, last year we had some 9-year-olds set up their own additive manufacturing setup from bits they found around the house, which is some of the ways that we're trying to get some of these younger people thinking about how they can construct infrastructure and make it work as well. So understanding the fundamentals of putting this together, some of that knowledge may not necessarily be at that year level in some instances. We do have the vocational ed component. So again, we've got Roger and the team from Partech who will actually be developing a program with how we actually collect, analyse and process waste materials into new products. So that will be one key piece as well. Tertiary programs are looking again in the middle of the room where the master's students. So some course material has already been embedded across science, engineering, and we have some stuff going into the education programs as well. I am going to focus on the summer program in a moment. And then lastly, we do have professional development as well. So we do have workshop series for anyone who wants to do CPD. Now, this is a little bit tiny, but in a couple of months, we will have our summer research program going. So the stipends for the students in this instance are actually supported by the grant. So they get to spend a summer with us. They get $5,000 tax-free for their troubles, and they get to learn to build a lot of different skills regarding turning materials into new products. Some of the engineering processes involve some of the testing capabilities that are required, and we do have our industry partners actually meet with them as well in a few instances during the summer. So those are supported by the grant. If anyone thought that they might want to have a summer student for 3 months focusing on a project of their choice, they're also welcome to come along, and we'll figure out how we can support that. But at the moment, we have space for 12 directly funded by the grant, and we have another 3 which are actually co-funded and supported by our faculty. So for those who are currently in the Masters of Engineering Science project, if you have research project A and B courses coming up, summer program is an ideal way in which you can actually do a heap of your assessment before you're even in the course. And I'm not saying you can relax during the year, but it will take a lot of the stress off you when you get a lot of the laboratory and engineering components figured out in an environment that is not assessment focused. So you're not stressing about that. So we've got the No Waste program, which focuses on what to do with particular waste streams. And then we have the Simple Hub program as well, which is more getting it in, I guess, moving on from the creative process and getting into the actual manufacturing a little bit more as well. So we have quite a few manufacturing partners on the Simple Hub project as well. And we're going to do some really creative things using particular waste streams for high-tech applications, which people aren't currently looking at the moment. So that's the summer program. The microprocessing capability I'll very quickly touch on because I'm looking at the time. So we are setting up infrastructure to enable actual industrial process to be occurring locally. And we're hoping the first instance will happen in the next 4 or 5 months, we hope, that we will have an actual circular economy set up across 2 to 3 partners in that instance. And lastly, just jumping into tranche 2. So we're focusing at the moment on close to home waste materials, but we do have our eye on a few other things. Now, there is a lot of work obviously being done in this space because everyone's jumping onto the challenge of what we do with our materials in future. And there's quite a lot of focus on pulling everything apart chemically and putting it back together. But there are some other clever ways that we can deal with this. So I am going to finish with this, because I'm going to visit the guys that did this research next year, where there was a Scientific American article recently where Trevor mentioned those wind turbine blades, and the focus in this instance was on the resin, not the fibre. A lot of research that is focused on things like large fibre composite structures like wind turbine blades tend to focus on recovery of the fibre, the carbon fibre, the glass fibre, and so on. But less attention's put on the resin, I guess, although that is changing. So often, burn away the resin, get your fibre. What are you going to do? But in this instance, they were looking at some very clever chemistry to actually break down the resin to make raw materials for other applications. So they were looking at PMMA, so your Perspex. The gummy bear one really caught my attention because my PhD was on extrusion of gummy confectionery. And I said, wait, how? And then it turned out that potassium lactate, which is not a gum reagent, but is an ingredient in gummy bears. And the funniest thing that I read in that article was the main researcher actually ate gummy bears made with the potassium lactate that he extracted from his resins just to prove a point. Okay, so this is where some of the future work is going. We are getting to the point now that our mechanical and our thermal recycling can only take us so far. Okay, the future is actually controlling how we might break down our molecules in clever ways to actually form feedstocks for quite a range of applications that you may not even thought of when you're just thinking of a fiberglass composite resin. So again, that's in Michigan State Uni, that work was done. So we were determining when the best weather time to visit was, because I heard it's not great. But we will have hopefully a little group going over there next year and thinking about how we can apply that to some of the work that we do here. And then very briefly, Simple Hub's getting going, focuses on manufacturing. The Impacts team is part of that one with the Sol thermal components. And we have a different range of partners on this project. And that's because our funders for both programs are the same department. So we need to demonstrate that they are clearly distinct but related programs of work as well. But that one's just getting underway. I've got less to report on that one. If anyone had any questions, and again, I am looking at the time because Hal is next up as well. I can probably take one question if anyone has any. And again, I'm staring at the students. If not, we will wrap up the day where I will hand over now to Wang, who is the theme leader for the functional materials group. And this is deliberately why I finished on that note, because he's focusing then on carbon fibre composites and their recycling.
My name is Wang. I'm the theme leader, the functional materials. In the functional material, that things we do have various different activities. That's including the flame retardant, carbon fiber composite, concrete and cement and concrete. And also we recently been awarded an ARC Future Fellow on the carbon dioxide conversion. But today I'm going to talk about one of the activities that was the carbon fiber composite. This year, 2022, actually is the 50 years milestone of carbon fiber composite in applications. So I'm going to, before I go to the presentation, I'm going to share with you the two pictures. So the first one is the latest Boeing 787 aircraft. In the aerospace industry, strength and lightweight is the most critical requirement. So the aircraft initially was made from the steel, and then is the much lighter aluminum alloy. And now these days, the aircraft, if you look at the latest larger aircraft, like the Boeing 787, Airbus 350s, 50% of the materials are made from the carbon fiber composite. So carbon fiber composite was very successfully used in the aerospace industry. The second picture, so you already seen today, many occasions, it's the wind turbine. We know energy is the world #1 pressing issues facing our current societies. Wind energy certainly is one of the few available options if we are talking about the renewable energies. And then I try to achieve the highest efficiency, economics, and then the wind turbine blade, it's become larger and larger. So these days we already see the turbine blade, the length is as long as 120 meters. It's such large blade, and then you don't want the blade hit to the pole. So the stiffness is become the issue. And then also there's a lightweight, the self-weight as well. So once we will come to this issue, and then some of the load bearing parts, we start to using the glass fiber, the carbon fiber composite to replace the glass fiber composite. Just try to increase the stiffness and then reduce the weight. I'd be surprised to know just this single application, the single parts using the carbon fiber composite. The usage of the carbon fiber composite, it's already exceeded the whole aerospace industry. Okay, now we come to the carbon fiber. So carbon fiber, that is the fibers. So the diameter is about 5 to 10 micron. So it's only 1/10 of the human hair. Most the material is the carbon atoms. So it's the carbon atoms. So carbon fiber, then you combine with the resins, we come with the carbon fiber composite. And then the material is lightweight and then extremely strong. the strength of the carbon fiber composite is 4 times stronger than the steel, 6 times stronger than the aluminum alloy. And then if you combine with the density, so the material density is only 1/4 of the steel, half of the aluminum. And then you combine with the strength and the density, we have a parameter we call specific strength. So carbon fiber composite, the specific strength is 16 times stronger than steel, 12 times stronger than aluminum alloy. So with this advantage of the carbon fiber composite, and if the application come with the strength and the lightweight is a requirement, and then carbon fiber composite is the solution. It has been widely used in the aerospace, defense, automotive, and all the other applications. The annual growth of the carbon fiber composite in this decade was 15 to 20% around the world. And then in China, it's over 30%. So certainly there's a large growth in this area. 50 years is a milestone. And then if we look back at the journey of the carbon fiber in applications, and then we can clearly see there's a 3 period. The first period was the, we call, it's the beginning stage. So the first 10 years, it's the beginning stage. And then that time, making the carbon fiber, and then also making the carbon fiber composite is extremely expensive. The only place they can afford to use the carbon fiber composite is a spacecraft, or some of the very, very high end of the sports equipment. And then with the development, then we come to the second stage. And then second stage is used in the aerospace. The application was triggered by the oil crisis, which is in the late 70s. The aerospace industry want their aircraft as light as possible. Then the industry started with the non-structural components, and then gradually move to the structural components, and then even go to the whole frame, main wing, and then the tail wings, all those. So that is about the 30 years in that period, from the 1980s to 2010. You see here, like from the 1980s, and then beginning was the non-structure, and then gradually go to the more significant usage, and then to the Boeing 787, Airbus 350s, and then you can see like it's a 50% of the usage. So we call that application in the aerospace, we call it's the first wave of the carbon fiber composite in application. There's several milestones in there. So after the initial development in the aerospace applications, and then in the 1990s, Tory and Boeing, they come to the arrangement. So now the Tory pre-preg was being fully adapted by the Boeing for this structural application. And then we mentioned about the 787. So that was come in the 2003. And then the Airbus 380 was the 2005. Both has over 50% of the carbon fiber composite. If we look at here, compared to the 767 and then 787, so initially the 767, a lot of parts to the aluminum alloy. And then you can see the aluminum alloy is a 77% in the whole structure. And then one can come to the Boeing 787s. So the main frame, main wings, and then the tail wings, all are carbon fiber composite, 50% of carbon fiber composite. In 2006, Boeing and Polly come to the long-term supply agreement. So they certainly use the carbon fiber as the main materials. Now, these days, we see the third one, the third period. The third period, which is started from this decade or last decade. And then we see the carbon fiber composite application is moving from the aerospace to non-aerospace industry applications. And then you can see these the volumes. So that purple area is the non-aerospace application. It is the 100 times more exponentially growth. So we see this one is the second wave of the carbon fiber composite application. And then we mentioned about these, the characters. Now go to the non-aerospace industry. Very significant characteristic is a large volume. And then also the industry, you have to have the low cost application, have to be low cost that can be accepted by those non-aerospace industries. So the application, you can see the wind energies, automotives, rail, and all this. We mentioned about the wind turbine blade, and then the parts here is the spark caps. So that just the black part, that small components, and then we use the carbon fiber composite to replace the glass fiber composite, and then you improve the stiffness 4 times. So with that part, then the whole wing blade, you have the 4 times stiffer than the glass fiber. And then use an example like this 57-meter long blade, you can have the 30% weight reduction. The success using the wind turbine blade, you can see the growth. So 2004, it's only 800 tons. And then you go to here last year, 30,000 tons. And then the 2025, you are going to see 80,000 tons. So it's going to be very significant growth there. What's the implication with moving the aerospace to the non-aerospace industry applications? We see the implication, and then those implications also represents the challenges for the research for the industry, and also represents the opportunities. So the first is the carbon fiber. We have to create the cheap carbon fiber to be accepted by the industry. And then, so that comes the large tow carbon fibers. So with the large tow carbon fiber, the efficiency increase, and then particularly the polymerization stage, you can reduce the cost 70%. And then the whole process, you can reduce 40% of the cost. So that particularly for the non-aerospace application, we come with these large tow carbon fibers. And then second is the matrix. In the aerospace industry, we usually use epoxy. That's the thermal set. And then epoxy has the problems with the processing. It's the autoclave, so it's a not continuous processing process. So it's the batch you put in once you already the form, the shape, and then you put the autoclave waiting for 24 hours at the temperature, at the pressure. And then second issue is the recyclability. Thermoset is not able to recycle once the cross-link is already made. So certainly people are talking about the thermal plastics. And then certainly there's two types of the thermoplastics, general plastics, so polypropylene, polyethylene, and then also the engineering plastics. And then the PEEK, PEEK, and then polycarbonate nylons here. There's with the thermoplastics, we need to do some treatment to make sure the carbon fiber can bonding the thermoplastic well. So in this part, we have done some of the work in our group. So that first is we know the matrix is a PEEK, and then we try to that's the process is the thermal treat the surface treatment is called fiber sizing, and then if we know the carbon fibers, you know the sizing what's about. One of the function is to create the interfacial bondings between the fiber and the matrix. So we know the matrix is going to be the PEEK. If you have the sizing agent is also PEEK, that certainly will good. Certainly there's some of the challenges because the PEEK is soluble. Mostly it's not soluble. So you need to create the intermediate phase first, and then finally after the hydrolysis, then you back to the PEEK. So that's the sizing. So we successfully created the PEEK sizing on the carbon fiber. And then the difference here, like without sizing, you only got the 40 megapascals, and now you can get 80. And then further, we adding the carbon nanotube into the sizing agent. So you further increase the strength, the strength there. And then also, if you do some treatment of the carbon fiber, here is the acetylene, some treatment, then you can make the carbon nanotubes more ready to distribute, avoid the agglomeration. So you further increase the strength, and then even you do the grafting of the PEEK onto the carbon nanotubes. Then we look at the mechanisms. The third implication is the manufacturing processes. So we said like in the aerospace, you use the autoclave, and then now you can use the injection moldings, compression molding, extrusions, all those thermoplastic the matrix manufacturing method. And then we also we also have the additive manufacturing. We have the picture here. So you use the additive manufacturing, you got the fiber, you got the resins, and then you also have this automated fiber placement. The fourth implementation is the recycle. So people already mentioned about the recycling, and then in the carbon fiber composite, there's the waste material. There has two. One is during the production. So during the production, about 20–30% of the carbon fibers is going to be waste. And then depends on which method you are using. And then the other one is the end of life waste. So you can see like from we're putting here like from the last 10 years, more and more carbon fibers, it's coming to the stage we need to do the recycling. And then show you like all those end of life products there. And then the group also did some of the research, and then we found that the pyrolysis probably is the most reliable, viable way. Depends on the economic and technologies. And then what we do is we adding some of catalyst to further reduce the pyrolysis temperatures from 600 to 360. So that means the energies you do the pyrolysis is lower, and also the recover the carbon fiber is better qualities. We wrote there's a paper particularly on the carbon fiber recycling and then carbon fiber composite recycling. And then there's several ways like stages you can do the multiple, like from the continuous carbon fiber in the aerospace, and then you can do the recycling, you go to the non-structural application, go to the automotive, and then even you go to the plastics you use as the filler. So you can have the several stages, and then that was mentioned in the paper. And then finally, we also the centers. I'm the editor-in-chief of the Composite journal, Composite Part B. So that is the highest impact factors journals in the composite areas. And then as the leading journals in the composite area, we do have several celebrations about this 50 years milestone of the carbon fibers. So that there's a special issues. So that's a future composite, particularly to celebrate the 50 years, and then global composite technology roadmap, carbon fiber composite as the lightweight solutions, additive manufacturing, composite recycling, thermoplastic composite. So there's several. Okay, so I know like I'm kind of sitting between you and the drink. So thank you.
Thanks, Hal. I know he mentioned he's sitting between you guys and drinks, but just checking if anyone has any questions, because I have a bunch, but I'll probably ask later. Questions for Hal about carbon fiber? Keen to get to the drinks, Hal. Okay, so there's plenty of opportunity to ask Hal a few questions in that instance. So, Shui Sen, just checking if you wanted to conclude the day.
Thank you very much for staying until the end of the today's event. Many thanks to all the speakers today. Excellent talks. I hope it's beneficial for you guys. And thanks the audience staying with us. Now we will move to the R block. So the bar is open with the alcohol drinks and the soft drinks. We can have more chat over the bar. Thank you very much. Have a nice evening. Thanks. So Punica is in Germany, yeah.